Hi everyone, and welcome to the fourth in a lecture series on social research methods. Today I would like to talk to you about the theory of sampling, and this is something that can seem, and in fact is, quite technical in certain ways. It's something that we'll pursue throughout the course of several lectures in this series, so I don't want you to worry if not all of this tracks at first. But there's several nice payoffs throughout this lecture, meaning that there are certain takeaways that I think are quite digestible and really interesting, and I hope that that provides some motivation to get through this lecture. So here's the plan. We are basically today going to talk about this phenomenon of sampling error here, and we'll talk a little bit about both sampling error and coverage error, really. And we'll talk about the properties of unbiasedness and minimal variance a little bit more. But I'll also say some more substantial things about sampling distributions, which are distributions that cover basically the theoretical and hypothetical universe of all possible samples, or sample statistics such as a mean or a correlation coefficient that you could take from a given population. This lecture will be mercifully short. I'm really just going to add a few points to our discussion of survey research from last time. And last time I mentioned that the step from sampling frame to sample needs its own commentary, so that's kind of what this step provides. But I'll also say a little bit about coverage error as well. It's kind of a combination of both, really. So here's a summary of the lecture. Biased sampling methods prevent good inference. Sometimes certain methods of biased sampling are useful for other purposes. For instance, if you have a procedure that is slightly biased but has a known low variance, that can be useful. So our example of a situation where we exclude or we top code, as it's sometimes called, the incomes of the super wealthy does produce a certain bias, but it also may reduce variance. There's other scenarios too, such as in qualitative research, where our purpose isn't necessarily to figure out a kind of ideal representative sample that we think is characteristic of the entire population, but maybe to observe a particular mechanism, such as that of social closure, meaning sort of the process of forming social groups that are well defined away from other groups. We might think, well, the way that, I'm going to use this running example because it's relatively benign, and probably everyone knows about the group. We might know that the Amish, for instance, are not representative of the population at large, and they're not even necessarily representative of other similar groups that maintain such practices with respect to technology, such as Hasidic Jewish people, for instance. But we might say, well, there's maybe some commonalities, though, and at a minimum, we just want to see what can be learned about this mechanism in this case, and maybe other researchers will later be able to fill in the gaps. So there are some reasons sometimes that you might want to use a biased sampling method, but for survey research, this is usually a bad idea. The key to unbiased samples, and by the way, unbiased again just means that the expected value of the sample statistics, such as the expected value of the sample mean, which is like the long run average of the mean in a sample, if you could take infinite samples, should be equal to the actual population mean, or the parameter. So for example, an unbiased estimator for the mean income of the US population means that the process by which we obtain a single sample, if we could do it over and over and over again, would give an average or a mean or an expectation. Those all mean the same thing. There's like a million different words for average, by the way, because it's such a common and useful thing. Some slight deviations in the meaning, but you get my point. So anyways, the expected value should be equal to the population mean of income. So that's what it means to be unbiased, just as a better review. The key thing here is to have some random element. The mathematical proof is a little bit complicated, but hopefully it's intuitive that a property such as a sample mean y bar should differ, that should be a random sample mean, should differ only by noise from the population mean mu y. So in other words, if we think about it, the kind of error term on any sample mean, should generally speaking be distributed in such a way that errors are more common the smaller that they are, they're less common the larger that they are. There's no particular reason that they should go in any one direction, so the expected value of the error term is 0. That's a common assumption that we make, and this is not just an assumption, but it's something that we actually can oftentimes motivate. So there's lots of reasons to suspect that if you are taking a lot of samples from a given population, Maybe it's useful to think about a simpler example, like say flipping a fair coin 10 times. If you did that over and over and over again, you're going to get an estimate of the true population probability, which is basically just a mean of the probability of flipping a heads. But there's not really much reason to suspect that any given set of 10 coin flips or any sample should differ in some particular way. And we have a strong intuition that we did this over and over and over again and then averaged out the mean of all those flips, we should get ideally 50% heads, 50% tails. So the reason that we would expect that is because it's a random sample. We don't have any particular reason to suggest or suspect that the mean in the sample will be any different from the population mean, and this means that in the long run, the procedure should be unbiased. It's possible to combine certain aspects of non-random sampling with random sampling, as in stratified or cluster sampling. This preserves, when you apply sample weights correctly, the unbiased component of the sampling process, and that's a good thing. But cluster or stratified sampling can also bring certain advantages that come from quota sampling, which is a kind of appealing procedure that doesn't actually work very well in practice. I'll say more about that in the lecture, but we can use certain elements of it in a way that's useful. These stratified or cluster samples are by far the most common type of sample in the real world. So even better about the sort of unbiased, the unbiased quality of a random sample is that random sampling processes often have sampling distributions. And those are those hypothetical long-run distributions of the sample statistic that are really mathematically nice. So for example, they might be normal distributions. This fact, the central limit theorem, is the foundation of inference. So the fact that pretty much anything that you can break down into means, so things like, for instance, a regression slope that we'll meet later on, you can apply this fact that the sampling distribution of that sample statistic across many samples is normal-ish, and normal means that bell curve or Gaussian shape. And a cool fact about that is that we know very much about the normal distribution, and so we can use this to our advantage. And even though we only have one sample, we can say that that sample came from a distribution. The distribution doesn't have to exist in the sense of literally there being some kind of universe that we could actually observe of all possible sample means. We simply happen to know that if we could do that, that's what it would look like. So any sample can be regarded as being drawn from that. And that's a really powerful fact. It's a little bit like saying we obviously can't, for instance, observe all possible sets of 10 coin flips because you could always add more. There's no way you could ever exhaust that. So you can't actually really plot the distribution, but it turns out, and in my kind of pure math class, we actually do prove this for the case of coin flips because it's a simpler case. It's what's known as a binomial process. It turns out that you can actually quite rigorously derive what that distribution would look like. So it's a cool fact. Okay, so let's dive right in. Let's start with biased methods of sampling, which might seem a little bit funny, but it's kind of useful to start with the way that we wouldn't want to do things, much as we did in the last lecture, so then we can talk about the way to correctly do things. So once again, let's assume that our statistic is mean income, and sorry that I didn't have the animation here. I know this is a little annoying to see all this at once, but just take your time with it. So the first type of sample that is common, and it is good to know these, by the way, because you'll see them referred to in the literature, will be a convenience sample. And this is a case where you just use people to whom you have easy access. So for example, you might go and ask people that you happen to know for a sample. This is what you'll do for your projects actually, but I'll say more about the practice in a little bit. Know that ideally we wouldn't do that, but sometimes we have to. So it could look like just using people that you know, or using people that happen to be congregated around a physical place. So maybe you go ask people their mean income at a Badger game, and that's going to be a sample that largely depends on the fact that most of us, at least part of the time, live in Madison. Sorry to those of us who are just visitors, but maybe sometime you'll make it down to Madison. If you go and ask people at a Badger game, it's certainly a good way to meet a lot of people, but this is obviously not a random sample. And it turns out this will be biased. So another option is snowball sampling. And again, this is actually a term of art in qualitative literature. It's not something that is necessarily wrong, but it can lead to problems when you try to use this to do inference. Snowball sampling is simply where you obtain a couple of contacts. Those contacts initially may not be pure convenience. They may be people who are members of a particular community, which you have a keen interest in, but then what you do is you ask individuals in that community to give you access to other individuals in the community and so on. Finally, you have a quota sample, and a quota sample is perhaps to novices the most appealing type of a non-random sample. You try to find a proportionate number of every type of person in the population and then interview them. This does have a really nice intuitive appeal, but it turns out, for reasons that I'll discuss later, this doesn't work very well. So generally all of these methods are biased. And again, just to reiterate what that means, because it's so important, it means that the mean of these samples, even if you could repeat the process over and over and over again, would differ in expectation from that of the actual population by non-random quantities. So for instance, we would typically expect that the mean income of individuals at a Badger game would probably be higher than that of the population of, say, the state of Wisconsin, in part because Badger games cost a certain amount of money. It primarily draws some individuals with some connection to the university, and those individuals will tend to have a bit of a wealthier background. That's maybe not the most extreme example. If you wish to think of a really extreme example, think about going to something like the New York Stock Exchange and trying to take a random sample on the floor of the stock exchange. That would be, in some respects, a random sample because the individuals in it are a subset of basically the people that congregate in that area. So one way to think about what's going on there is even when you have a random sample in some respect, you're actually sampling from a different and more limited population. But some of these other methods have technical problems that are even a little bit beyond that. So for instance, in some cases, you might have a group of people, like let's say a convenience sample. This could be people who may in some respect be a random subset of the population. Like if you go to a grocery store in a middle income neighborhood, you might obtain people who in certain ways are not a particularly biased sample of the population, but you might also have this issue that, say, the individuals in the sample have a relationship to one another. They're not independent. And this can cause certain problems as well. So we won't go too deep into the theory there, but I hope that that provides some overview of the common ways that people sample and the things that are wrong with it. For the most part, what you need to watch out for here is that in all of these cases, whether it's a convenience sample, a snowball sample, or a quota sample, oftentimes what you're doing is actually sampling from a different population than the one to which you want to generalize. That may not actually be obvious in the case of quota sampling, so let's talk about that. So quota sampling seems like a good idea at first, and I want to bring this method home a little bit more. So why don't quota samples work? And this will actually lead us into an interesting discussion of the correct version of quota sampling. It seems like a good idea at first, but it fails because there's no clear point at which one should stop stratifying. So what I mean by that is when you try to include one of every type of person, this is awfully hard to kind of figure out because when do you stop deciding what are the components of a person's personality? You might want their race and their gender and their religion and their class and their level of education, and you can see that there's no obvious point at which I should stop. And number two, it offers no algorithm for picking within those strata. So for instance, in classic quota sampling methods, people are typically pulled from these groups, but once they're admitted into the survey, or once someone, like let's say once you come up with the types of people you want in the survey, the individuals that you obtain from those strata or those groups, typically there was just no method at all. It was dependent on, say, the people that the researcher knew, so it would oversample well-to-do professionals, even if they're proportionate to different demographic groups. So you can take a look at this page for some more details. This is a nice write-up. You saw this in the Salgonic reading, though, but the most famous example of this is a president from my home city. This is Truman, of course, which when I teach this class in SOC360, or teach this photo, I've learned that only about 5% of people know who this is. So this is Harry Truman, who was president after FDR. FDR's vice president. Kind of an interesting character. I actually went to the Truman Museum and spent an entire day there over winter break with my mother, which was a really good time. But he was kind of an interesting, complex figure. Anyways, you can see here, this is from the battle days when newspapers had to go to print the night before. This is Mr. Truman after he won the election. He's having a big laugh at the fact that the Chicago Daily Tribune boldly miscalled the election. And this was kind of the final blow, as you can read about in Salgonik's text, for quota sampling, because basically, again, Dewey would have been the candidate that maybe was more favored by individuals. You can see here that he was the GOP or the Republican candidate, may have been favored by individuals who were a little bit wealthier. At that point in U.S. history, the GOP was considered to be significantly more the party of the well-off. There's been a bit of a change in that fact. But anyways, that probably has quite a bit to do with the quota sampling method that these papers employed. So now let's begin our discussion of unbiased sampling methods, those for which the expected value of the sample mean from this process. Again, remember that the sample mean is a random variable, so we actually observe a particular sample mean, but it comes from a process, and that process has some randomness baked in. We want to know about the processes where we expect the value of the sample mean to be equivalent to the population mean, and this generalizes in many situations. Again, the case of regression slopes is an important extension, but we'll stick with sample means for the sake of simplicity. So there are three primary types which I want to tell you about today. The first is the one you're probably most familiar with, known as the simple random sample. Basically, you select people at random from the population. It does what it says on the tin, as they say in Britain. The important properties here are that you have what are known as IID random variables. So what that means is that you can consider each person in the sample before they are drawn. So before you actually fix a particular person, you just think about person one in their abstractness. That random variable, because person one could be anyone, person two could be anyone, those variables should be independent, meaning that the probability of selecting person two doesn't depend on the selection of person one. And they should be identically distributed, which means that their property in question, say the income, comes from the same distribution. Now, that's actually not super realistic in one respect, because when we take people in a sample, we don't reuse people. So we have sampling without replacement, as it's known, meaning that once you select someone into the sample, then you select another person. You can't typically select that same first person twice. That's just disallowed, even though in theory you could do that. You could have a sample where you're willing to say, yeah, this person just very freak coincidence happened to end up being called twice, and we'll include them both times. But when populations are very large and the distribution doesn't change really at all from any practical standpoint, when you remove one person from it, then it's basically the same distribution when you take the 1,000th person in the sample as it was when you took the first person. So that's a kind of a long digression, although these are important concepts, and this is the most kind of fundamental type of sample. So our next unbiased sampling method is what's known as a stratified random sample, and this occurs when we select groups that we definitely want to be in the sample, and then we sample randomly from within those groups. So we preserve the random element, which makes sure that the estimates for these subsample groups are unbiased. Then we have this non-random component, which is that we definitely include certain groups within the sample. And the reasons for this are, there's actually a number of different reasons. One of them is that you might want to have adequate subsample sizes so that if you have groups that are numerically small, you have an adequate number of people to do statistical inference, because a minimum sample size is necessary for that. So sometimes groups, to use the kind of running example that I've used before when I've referred to this, sometimes if you get a random sample of, say, people, and you want to ask them about their income, and you want to make sure that you have enough to estimate the mean income also for every U.S. state, it might be difficult to do this for, say, Wyoming, if you just sample randomly and you only take a simple random sample of, say, about 1,000 people. The subsample size for Wyoming respondents will be very small, and it might be too small to permit much further analysis. Another possibility here is illustrated by this table on the right from Bryman's text, you can see here that he's actually up to something a little bit different here. Here, he's not just making sure that he has an adequate subsample size, but he's actually making sure that the sample has proportionate representation of different groups, which is useful for a variety of reasons. So, for instance, in this case, you can see that individuals from these majors, like the social sciences, had 1,200 people at this, I think, lightly fictionalized university, and that was out of 9,000 people. If you calculate that ratio, that happens to be about 13 1/3%. And in the stratified sample, 60 out of 450 also happens to be about 13%. In this hypothetical simple random sample, you might have population sizes that differ a little bit from their size in the hypothetical sample sizes that differ a little bit from their actual size in the population. So even though you can treat that in different ways, for instance, you could come up with a range of estimates for the share that a given group makes up of the population, there are a variety of reasons why you might want to have exact representation, especially if you happen to know, for instance, that certain big groups like race or gender, you may have reliable population data on how much of the population those groups comprise, and then you might as well try to make those proportionate, and then you'll let randomness govern, say, other types of questions that may be unknown. So the US government, for instance, doesn't collect census information on people's psychometric qualities. So those are things where we'll just need to basically sample randomly from within groups. We're not going to stratify on something like the number of people who are diagnosed with depression or something like that. But for these big population groups, oftentimes that's more efficient. We also have sometimes what are known as multi-stage cluster samples. These are basically like stratified random samples, except there's a little bit of a difference. They're similar in that we start with guaranteed groups for inclusion. So for instance, we might, in a lot of cases, pick first of all, a cluster is basically a geographic area in most cases. And the kind of logic here is that it's inefficient very often to sort people or go ahead and survey people from all different places in the country. And so, sometimes if you don't have access to a telephone or you need to do part of the interview in person, you'll not be really capable of actually randomly sampling because you would need to go to the farthest reaches of the country to do so. For instance, if you get a census block list and then you assign the blocks random numbers and then go to those places, you may have to be schlepping it all the way up to Fairbanks, Alaska, let's say, and that wouldn't necessarily be a good thing. So what you can do with cluster sampling is you can pick, as is typical, certain groups that are necessary to include. So a lot of times those are New York and Los Angeles in actual cluster samples just because there's such massive population centers. And then from there, you can pick other clusters. So, and you can pick them randomly, and you can figure out what their probability of inclusion was, and then adjust for it later. So clusters are typically these neutral geographic units, and strata are usually distinct social statuses. The clusters don't all have to appear in the sample. The point is just that you sample the clusters so that you cut down on some of the cost, and then you adjust for the differential probability of inclusion based on the size of the cluster. These things are really dense at the highest level, and they're not going to be important in our class, but I did want to apprise you of their existence because, as I mentioned before, this is how actual samples work in the real world. We rarely see simple random samples. I think I'll probably try to mention at a later date a little more information about the California Health Survey, which is a rare example of an almost pure random sample that is out there in the real world, but most actual random samples are random samples from within strata or clusters, making them not simple random samples. So let's talk a little bit more about stratified random samples so that you understand more fully what these things are. So again, these have an element of quota sampling. We start with certain groups that we want to make sure we include, and sometimes then we'll also even make sure that we get a certain number of people from within that group. But in other cases, you may also let the numbers vary somewhat, but you make sure that you include at least some people from a particular group. In some cases, if a population is, say, only 1 or 2% of the the subpopulation is only 1 or 2% of the total population, simple random samples of a given size might fail to include any such individuals just by coincidence. So what we do to come up with these estimates is we break the population into these strata. So again, these are things like race, class, gender, etc. Then we sample randomly from within, and we can take different shares from each group to get our desired subsample sizes. So for instance, we might aim to sample about 1/10,000th of the say white male population, but we might aim to sample say 1/5,000th of the say black female population. 1/10,000th is actually a giant sample, by the way, for the US population. So it's very often much less than that, but I don't want to use giant numbers. So then what we do at that point is combine. We generally oversample these small groups to ensure those minimum sample sizes. So then what we need to do is we need to weight people from those groups at the end to undo this overrepresentation. So we will have a higher probability of including, in the example I gave before, black female respondents. So we need to, at the very end of the analysis, account for the fact that they are actually a smaller share of the population than they may be in our sample. This is how most actual samples work. So here's an example of how some of these stratified random samples actually work in the real world. So the GSS and the CPS, from which I'll often pull data, in fact, I've already shown you quite a bit of data from both of those surveys, more the GSS, but I'll show the CPS later, are stratified random samples. And you can read a little bit here about how this is actually done. The details aren't super important for us, but this is just good so that you have an actual concrete example and not just me describing it. So I'll read a little bit of this because it's actually quite interesting, I think. So for instance, the GSS has a multi-stage area probability sample to the block or segment level. That's a whole lot of jargon that basically means there's a bunch of different geographic units, so there's some cluster element here as well. You have what are known as primary sampling units, which are the standard metropolitan statistical areas, which are basically the US government definition of what regions are effectively. And then you can actually stratify these primary sampling units by region, ACE, and RAGE before selection. So you've got this kind of cluster dimension, which is this whole set of geographic areas, but then you've got a strata stratification on these strata, region, age, and race also. And then you have a whole bunch of other kind of details here where they subsample within the different PSUs and so on. Those details aren't super important for us, but just so you know, this is how actual random samples work in practice. There's a strong non-random component, but it's very important that there is some random component so that the magic of random samples, which is the final topic of this lecture, into which we'll turn in a moment, comes to pass. This is from the GSS 2019 Codebook Appendix A, by the way. There's a longer discussion here, but again, this is not super important for us in this class. So what is important for us in this class before I turn to the magic of random samples? So your samples won't be random samples. True randomness is hard, but that said, we'll at least somewhat diverge from pure convenience samples given that we have research teams rather than individuals. So it won't be the case that we have a pure convenience sample where it's just the people that a person in your group knows. It'll be people that everyone in your group knows, most likely. I recommend just sending this to family and friends, or use with politeness and good judgment, use listservs that you're on. If you have seen such emails on that listserv before, for instance, that's probably a good sign that you're allowed to use it for that purpose. Please don't sully my name by spamming unrelated listservs where that wouldn't be cool. But there's probably a lot of kind of group threads that you have access to where you see things like this occasionally, and that's also a good method. I will also tweet these things out from my professional account as well, just since occasionally friends of mine or colleagues of mine will answer these. So we'll get a good mix. You can define your population narrowly, by the way, as well. So for instance, you could say that your population is all UW-Madison students. That's fairly specific, but it's still general enough that it's of interest. It's not just the group of people that I got. And that may well be the case that you want to use this population if you plan to mostly ask fellow students. It depends on who you plan to ask, but this is one way to get a sample that's actually not really that different to a random sample of the population. It's still people that you happen to personally know. There's still some major deviations from randomness, but it's not as grievous as, say, saying that your population is the US population. There's no need to use weights in your projects, by the way. This is just the information about weights is just because that's how virtually all samples work in the real world. The final point, what I'm about to say about the beauty of random samples really only applies with random samples. You should just know this stuff, but it's okay that it doesn't strictly apply to your case. It also applies to any correctly weighted semi-random sample of the types that we were discussing before, by the way. So let's move to the beauty of random samples. So this is the beauty of random samples, and we've already seen this graphic before. So this is a simulation of the sampling distribution for sample means from the US population of mother's education, or the mean of mother's education. So the mean education of everyone's mother in the United States, which is not exactly a good estimator for the mean education of women, but it's a quantity that's maybe just of interest, like the mean education of people, women specifically who have had children, for example. So here I simulated this. I basically used a large sample, the GSS, as the population, quote unquote, and then I took subsamples of size 20 and size 100 just to show the difference, and then I iterated that process 5,000 times. We don't actually get to do that in reality, so we don't actually get to take 5,000 samples of our population of interest. That would be enormously time consuming. And what's more, we wouldn't really learn that much from it because you can see, and I didn't really call that much attention to it in the past lecture, but you can see here that these sample means, when plotted, even though the red ones have a higher variance, and even though they could be biased, although they happen not to be, in any case, they have these really nice shapes. And those really nice shapes can actually be described mathematically through the use of functions. And you may know this, that these bell curve shapes are formally known as normal probability density functions, or just generally normal curves, but in this case, they're probability density functions. And this is a curve or a function that we know an enormous amount about, and it's also very regular and has really nice properties that are easy to describe. So we know a lot about the mathematical details, but they're also very appealing to most people because they're simple to describe and there's all kinds of cool facts about them that I'll mention in a moment. So the fact that sample means have this normal distribution, which you can derive abstractly, or you can just observe that when you simulate taking very many sample means, which you can do, again, as I mentioned, like if you have a large data set, you can do this on a small scale by sampling your data set, which is called bootstrapping, which is useful for a lot of purposes. But when you can simulate that process, we get the same results. In particular, with this large sample size, n equal to 100, you can see if you overlaid a normal curve on this, it would be an almost perfect fit. It's really quite remarkable. So these are two of the really key properties of random samples. Their distribution follows a well-known function, the normal, and it has a known variance. So going back to our discussion of bias and variance, since random samples are also unbiased, in most cases, there's some caveats that I don't need to mention here. That means that our sample error is just a function of the variance, and we know that variance. So that's really cool stuff because it means that we can actually quantify, in most cases, the likely range of difference of our estimate to the true parameter that we care about. That's the foundation of inference, and that's a very cool fact. And today, I'll just show you a brief glimpse at where we're going next week and in following weeks. So I just said all this stuff out loud. Let's kind of describe a little bit more formally what's going on here. And again, do note that this holds with some small changes that we don't need to worry about for stratified random samples as well. The key thing is that you have randomness at some point, which involves basically what you might call the law of error, meaning that at some point, the way you select samples means that the sample mean will only differ from the population mean once you apply the weights by random noise. And that means that they have this nice curve. The Gaussian distribution, for instance, is closely related to what's called the error function, and it gets its name from the fact that it arises from processes. It's got a formal mathematical definition, but it is characteristic of processes governed by random error. So you can see here, there's this other kind of really interesting fact that I haven't already mentioned yet, which is the central limit theorem. And the central limit theorem is a very cool thing. It tells us that sample means are normally distributed, which we already saw before, but that this holds even if the population distribution itself is not normal. So I haven't actually shown you so far what the distribution of mother's education looks like in the population, quote unquote, which is really a sample, but I'm doing that just because we don't actually have population level data on most things. So I'm using a large sample as the population and then treating subsamples as my samples. I won't keep saying that because it can be confusing, but just so you know for the record. So what's happening here? We've got the distribution in pink here of mother's education in the population, quote unquote. You can see that it's distinctly non-normal. So there's one peak here, but then there's a couple other peaks, but those other peaks are both to the right of the largest peak. And then to the left, we have this kind of longer tail, but we don't have any obvious peaks. So however you characterize this distribution, it's not normal. However, we see that the distribution of sample means, which I plotted atop it, is strongly normal. And this is the sample means from the same process as before. So what that means, or what we could say more generally, is that sample means come from a sampling distribution that is normal in its properties, normal in the specific sense of coming from a normal distribution, even when the underlying population distribution is not normal. You have to be careful when the underlying population distribution is strongly non-normal. Mother's education here is not strongly non-normal. But the nice thing is that as long as it's not a totally wacky population distribution, this central limit theorem basically holds, which is a really amazing fact, I think. Although it's actually quite intuitive as well, because the sample means are basically governed by a strong central tendency and then random error. And that's not necessarily the case for the actual underlying population variable. But the sample means, so this group level property, are governed by that random error. By the way, I've already mentioned this term before, but let's formally define this sampling distribution. The distribution of all possible sample means is what we mean by the sampling distribution. It's important to stress that this is kind of a meta distribution. So it's the distribution not of a variable that we directly care about, like mom's education, but sample means thereof. And this, in a certain kind of formal probabilistic sense or probability theory sense, this really doesn't matter that much. They're just both distributions and we can characterize them in different ways. But I have found that people find this very confusing at first. This is what I found confusing about statistics at first. They're really different types of distributions, and sometimes pure mathematicians don't appreciate how strange this can be. So I do appreciate that, and I want to stress it to you all. This distribution we see here in this sample, mother's education in the sample in pink here, or I'm sorry, in the overall population, pardon me, not in the sample, in the population is a distribution in the normal sense that we've probably understood it up until this point before this class. It shows us basically the relative frequencies of different values of the variable mother's education. This sampling distribution here is something that we don't actually need to observe in reality. Again, I'm producing this through a simulation, but that's not how we actually do things. I'm just doing it to prove the point. So the sampling distribution is a hypothetical thing. You actually only are going to observe one sample mean most of the time, and all you need to know is that that sample mean comes from this hypothetical probability distribution. That distribution doesn't have to actually exist in the sense of all of these sample means existing for us to know that a sample mean is drawn from it, which is kind of a trippy fact. Hopefully you can appreciate it as sort of an interesting, fun thing, but I do understand that it can be confusing, and that's what this second point says here. So let me also mention now a couple of other key facts about the central limit theorem before I show you basically a little bit about what we do with these things. So some other facts that we'll revisit later. The variance of a sampling distribution is a function of two things. It's the variance of the population standard deviation, which we denote sigma squared. Don't worry about that. We'll learn the notation later. And the sample size n. And it happens to be the case that the formula is very simple. The variance of the sampling distribution for means is sigma squared, or the variance, over n. Sigma lowercase means standard deviation, by the way, and standard deviation is just the root of the variance. The variance is less intuitive, but it's mathematically simpler because there's not a square root involved. So we'll typically use the variance when we're doing these proofs. The central limit theorem is also only true when n is not tiny, let's say larger than 20. If we don't know the population variance, sigma squared, we have to estimate it with the sample variance, which we write S squared. This does cause some complications, but these are really only minor complications.